Hello, this is Limassol, Cyprus, the European Union Nano Safety Cluster NanoWeek and NanoCommons final conference. We are having the training day, the Thursday of the week, which was June 23rd. And in session 4, we were tackling nanomaterials grouping in practice, getting really very interactively, selecting and applying nanotoxicity hypothesis. The trainers of this session were Hallie Johnston, supported online by Fiona Murphy, Vicky Stone from Heriot-Watt University, and Mario Pink, who was supported online by Andrea Hase from the BFR in Berlin. The objectives, the grouping framework, the basics of it per se, and then a couple of case studies of different nanomaterials in a very interactive way played through these cases, interactive with the audience present at Limassol.
First, Eleanor Johnston from Heriot-Watt University is going to give us an insight in the grouping concept, basically, from Gracious. It's not the only one existing, right? But I guess it's a very educational session that we are looking forward to now. And at any time, come up with questions also in the chat. We will have a little bit an eye on that. And we will try to do this as interactively as possible. And Mario is then from the BFR in Berlin, is then also going to take this into a specific case study on regulatory context. So have fun and be interactive, and let's learn a lot about how to group. I mean, this is really important. I also want to stress this, and this is the reason why we put it here, because we cannot test everything. We had this said already today, this morning. We cannot test everything. We need to eventually learn from one thing to the next, this so-called read across. And this is just possible if you know, if you human have always learned by putting things into different drawers. The first thing you learn in biology is these are the birds and these are whatever. This is the lion, and you put into different categories, right? And just the granularity of these different categories, this is actually the thing that we're talking about now, right? Good.
Thank you, Martin. So as Martin said, please interrupt as we work our way through the presentation. If you have questions, there's a few interactive elements, so feel free. There's not very many of us, so you can hopefully just shout out. But yeah, I'm just going to start by just giving a brief overview into what grouping is, why we need it, what we've done to develop grouping approaches, and help give a little bit of insight how this can help us progress towards making substances more safer and sustainable. So most of the work that I'll talk to you about today was conducted as part of the EU project Gracious, but now within the ongoing project Sunshine, we've taken forward quite a few of the concepts that we developed and are building on these. So I'm sure most of you are aware of what risk assessment is and what challenges are associated with assessing the risk of chemicals. So when we want to determine the likelihood of a chemical causing an adverse effect, it's quite challenging. We require quite a lot of information, and essentially we have to combine hazard and exposure data. So I'm sure I don't need to explain what hazard is to a lot of you, but we're looking to see what adverse effects our substances can cause. So we have a number of different endpoints that we might investigate in our hazard studies, and we're interested in seeing what's the impact of these substances on human health, but also the environment. And there's a lot of different models that we have available to us that allow us to try and predict this toxic effect. It's also really important that we consider the hazards following different routes of exposure or release into different environmental compartments. So that's the kind of hazard side of the risk assessment. For exposure assessments, again, there's a number of questions that we like to ask and a lot of information that we need to gather. So what are people exposed to? Who is exposed? Are they susceptible? Or is there any susceptible groups? You know, where are they exposed? Is it in a workplace? Is it in the environment? Is it as a consumer? You know, so we have this list of questions that help inform that exposure. And more often than not, we're estimating an exposure. We're trying to model and predict what that exposure will be, but we can get measurements as well that can feed into this risk assessment. So obviously there's a lot of chemicals being produced and used. There's a huge diversity. They vary with respect to their physical chemical properties. They're used across a number of different products by a number of different sectors. So all these chemicals will require a risk assessment. And there's thousands and thousands of them whose risk needs to be assessed. So within Europe, we have REACH, the regulation that's responsible for protecting human health and the environment from the risks that are posed by chemicals. And any chemical needs to be registered by the companies that are producing them. So this means that we're collecting data on their hazard, on their properties, that is accessible to everyone. So if we looked back in March here, and there was over 26,000 chemicals that were registered. So you can imagine this is a huge amount of chemicals whose risk needs to be assessed. The other issue with risk assessments, and particularly the hazard side of things, is that particularly for human health, we're relying on rodent studies. So there's a lot of ethical implications associated with this work. Lots of animals are used. This also costs a lot of money, takes a lot of time, and there's often questions raised about whether or not rodents can actually predict a human response due to species differences. So it's clear we need alternatives. And actually, REACH promotes the use of non-rodent models or alternative models when we perform risk assessments. And the aim is to make testing more ethical, but also to make it quicker, cheaper, and more predictive. So this is where grouping comes into the risk assessment process. So grouping might be quite a novel concept for you. I'm not sure how familiar you all are with grouping, but conventionally, if you had a chemical and you wanted to assess its risk, you look at it individually. So you're performing risk assessments on a case-by-case basis. And as we've mentioned, this has a number of implications ethically, financially, and resource-wise. So we're trying to look at approaches that will improve the risk assessment process. And grouping could be a way of doing this. So when you perform grouping, you're trying to develop more intelligent and streamlined ways of gathering information for risk assessment. So you have to identify substances that are similar, and then you group them. So you have this group, and not all of these group members will require hazard testing to be performed. So you can try and predict what toxicity your members of the group will have based on existing information. So the next slide provides you with a bit more information on that process. So essentially, if you can establish a group of similar substances, so similar is the important word here, they have to be similar perhaps in their physical chemical properties or the hazard or their fate. If you can establish this group, you can apply something called read across. So again, this might be a bit of a novel concept to some of you, but this means that if you have information for a chemical whose risk has already been assessed, so there's already extensive information available on its hazard, you can use that existing information from that substance to fill gaps for a substance which lacks data. So it's data poor. So it just means you're trying to make predictions about what hazard that data poor substance will have. And this is a way of, as I've mentioned, reducing our reliance on animal testing. And actually, this is something that is encouraged by the regulators. So hopefully you've all heard of ECHA before, but this is the European Chemicals Agency. And they're responsible for implementing REACH, this regulation that's concerned with protecting human health and the environment from the adverse effects of chemicals. So the number of guidance documents have been published by ECHA that explain what grouping is, that provide guidance on how grouping should be performed. And what they recommend is that there's this stepwise approach. So in order to justify grouping, you need to be quite transparent in why you're doing this. So you need to be also very systematic. So I know it's difficult for you to see the detail on the slide here, but it provides these different steps in the grouping process. So it's saying you have to develop a grouping hypothesis. So you have to suggest why these substances are similar, why they're all members of the same group. You then have to gather available information relating to their physical chemical properties, to their fate, to their hazard, and then you fill the data gaps. So it's this read across process that I spoke about. So it's quite logical, it follows this different series of events, but there's not much information on how to do this. So it says what you should do, but not necessarily how you should gather all that information that you require. And this is where kind of our work comes in. So we're going to start with a non-chemical example now, but it's just to get us thinking about grouping more generally. So I want you to have a think about what information would you need to group similar substances? What would you need to know in order to identify if you could form a group? So on the slide here, we have these different, I'll call them blades, knives. And so we want to identify what you would be thinking about to try and group them. So we have a Menti room here. You can see the login details at the bottom. So in the room, you can either use Menti or you can shout out, whatever you prefer. But it's just having a think about what would you want to know about these materials, these blades. Hopefully some answers will start appearing soon.
Do you have fresh?
So I'm not very good with the technology. It's not working. Oh, here we go. Size, and it's come up really big appropriately. So yeah, what is the size of these different materials? Yeah. Yep, the blade. Yeah, so some might be smaller than others, some might be larger. Yep, their weight. So you can see quite a lot of these suggestions that are being provided are kind of the characteristics, if you like. No, we're not talking about chemicals here, but you want to know about their appearance, their size, what they're made of, what their length is, how sharp they are. So it's kind of their characteristics. What else would you want to know about them? So do you think they'll all cause the same harm? Yeah, so the application here is really important because it might tell you who's going to be working with them, who might be exposed to them, if you like. So are they being used in a workplace? Is it someone in their home? You know, why are they being used? Yeah, exactly. How, you know, one of them might be able to chop off your head, one just your finger. So, you know, what kind of harmful effect? Yeah. So, you know, this is, you know, we're not talking about chemicals here, but actually a lot of the things that are coming up on the slide here would actually be relevant to grouping of chemicals. You'd want to know who was using them, what they were used for, what properties they have. So some really good suggestions provided here. Just trying to see if we've missed anything. I think we've covered most of this. Thank you for participating. My students don't always do this, so it's much appreciated. Okay, how do I get it back to the full screen? Okay. Oops. Okay, perfect. So we have a few, you know, I predicted kind of what you said here. I think we've covered most of it. You know, their characteristics, their settings that they're used in, who will use them. So that's more the kind of exposure side of things, what adverse effects they cause. And, you know, just by looking at them, we could potentially form these groups. So this is quite arbitrary, you know, but it's just to help put in context what, you know, what you would think about if you wanted to perform grouping. So now we're going to move on to nanomaterials. So I don't need to convince you that there's lots of nanomaterials available. We need to assess their risk, and we can't do this on an individual basis. We need ways to avoid assessing risk on a case-by-case basis, and grouping might be the answer to this. So within the project Gracious, we developed this framework that was all about developing ways of grouping nanomaterials and performing read across to our question.
So it's a training session. So I have to do that, and I also try to encourage this kind of thing. We talked about such type of thing this morning already. There was this comment from Sean in the first session that safe by design means we don't know it yet. We do not have the data. So we need to transfer from somewhere else to be able to say something about the future. It's this kind of forward-looking aspect that we need. So therefore, the grouping would be a very relevant step into this direction. So I just wanted to make again this kind of cross discussion.
Perfect. And yeah, as we work our way through, please interrupt us if you have any questions. So this is the design of the Gracious framework. It looks quite complicated if you see it, but we'll go through it step by step now, and then we'll pick out different points of it to discuss in a bit more detail over the next few slides. So this framework that we've developed allows you to group similar nanomaterials. So the first thing that we ask the user of the framework to do is to identify what nanomaterial they want to group, or they might have a panel of different nanomaterials that they want to consider. So that's the first step. The next thing is then to provide us with some basic information, or provide the framework with some basic information on their material. So we ask for some information on the physical chemical properties of the nanomaterial. So this could be predicted. So if you're in the design phase of developing a nanomaterial, it could be that you're making predictions about the properties you want it to have, or you could have measurements on your material. So you have to provide that information. You then have to think about why you're performing grouping. So is it for a regulatory reason? Is it to submit information to REACH, for example? Or are you doing it to introduce mitigation measures within a workplace? Are you using it to inform safety by design? So have a think about why you want to group this nanomaterial. And then provide information on how that nanomaterial is used and what exposure might be expected to it. So you feed in all this information, and then we consider what grouping hypotheses we want to test. So one thing that ECHA is quite strong about is stipulating that a grouping decision must be hypothesis-driven and evidence-based. So it's really important that you formulate hypotheses that allow you to group your nanomaterials. So we've actually constructed quite a few grouping hypotheses, and I'll explain a bit more about these in a second, but we have a list of hypotheses that the framework can help shortlist for you. So it's saying it has these properties, you expect exposure via a particular route, so these are the grouping hypotheses that you should prioritize assessing. And then what you do is use something called IATAs. Again, we'll come back to these, I'll explain what they are, but they're decision trees essentially that ask you questions in order to help you make that grouping decision. So by answering the questions in this decision tree, it allows you to accept or reject that grouping hypothesis. So we do encourage people to use information that they already have, but if you do need to gather more information to help accept or reject the hypothesis, we tell people what testing should be performed. And within these testing strategies, they're tiered. So we suggest that you start with more simple or basic tests and then progress to more complex models. So it's all about trying to, again, reduce our reliance on animal testing. So that's a very quick overview. There is a publication available, but I'm going to talk about a few of these elements in a bit more detail. But I really would encourage you to read this publication if you want to learn in depth more about the Gracious framework. So I mentioned that we have to have hypothesis-driven grouping decisions being made. So it's quite difficult to actually formulate a grouping hypothesis. You know, how do you word it? What do you have to consider as part of that hypothesis? So we've developed a template to do this. So it just helps point out what considerations you should make if you want to perform grouping. And it's split into a number of different elements here. So the first thing you would consider, and I've discussed this previously, is of why you're performing grouping. It just helps put that grouping grouping hypothesis into context. You then have to consider the life cycle of that nanomaterial. So you're considering what is the exposure to this nanomaterial expected to be? Is it humans? Is it the environment? Who's going to expose, or what environmental compartments? What are they exposed to? What's the frequency of exposure? So you're thinking about how humans or the environment will be exposed. You're also considering what they are, so the physical chemical properties of the members of that group, and the fate. So once a human has been exposed or environmental compartment, what is the fate of that nanomaterial? And then lastly, what is the hazard? What are they going to do? So I'll show you examples in a few slides' time. But as I mentioned, we have 40 of these hypotheses that we've already developed. We call them predefined grouping hypotheses. It's just the ones that we have formulated as part of this project. And they link the physical chemical properties of nanomaterials to their fate and their toxicity. As I said, they're relevant to both human health and the environment. They cover different routes of exposure of humans, like inhalation, ingestion, and dermal exposure. and they also cover release into different environmental compartments. So we've been able to develop these hypotheses just due to the amount of available information that is already available within the existing literature. So there's a lot of evidence to support their formulation. And importantly, the list can grow over time. So it doesn't have to remain at 40 hypotheses. Over time, we can develop more of these grouping hypotheses as we get more evidence to support their development. So here's a few examples. They're quite wordy, so we've kind of emphasized the important parts within the orange text here. So these hypotheses all relate to human health. And hopefully what you can see is they relate to different routes of exposure. So the first one relates to inhalation, and you can see this is specifically mentioned within the hypothesis. The next one relates to dermal exposure, and we have oral exposure here. So each exposure route actually has quite a few different hypotheses that have been developed. These are just some examples. So you can see we tell you what properties, or physical chemical properties, the material needs to have. So you can see that these all relate to the dissolution of the nanomaterial, so solubility. So is it going to be quickly dissolving, instantly dissolving, or partially dissolving? And then it links it to a toxic response. And we also do consider the fate. We've also formulated some hypotheses for the environment as well. So again, you can see where we identify what physical chemical properties the material will have. You can see here it relates to dissolution rate. We have surface treatments mentioned in the second hypothesis. And again, we're looking at the fate and toxicity. So lots of these have been developed, and it allows people to test these hypotheses if they want to perform grouping. And as I mentioned, the way that you gather the information you need to make a grouping decision is that you use IATAs. So these are called integrated approaches to testing and assessment. And this is how they're structured. It's like a decision tree. So each of these blue boxes we would call a decision node. So it's asking a question. And so you can see it's asking about exposure here, physical chemical characteristics. And if you answer yes, you keep working your way through the questions. And ultimately, if you get to the end of the IATA, you can accept the grouping hypothesis. If you answer no to any of these questions, you can't accept the grouping hypothesis. It's rejected. And we'll show you specific examples of these relating to the hypotheses that I've just shown you, so you get more of a flavour about what questions you would ask. So these decision trees allow you to gather information. So they're telling you what information you need to make a grouping decision. And you can, as I said, use existing information, so information you already have on that material, or you can generate new data in order to answer these questions. What's really useful as well is that you can start to populate a data matrix. So this just means for each decision node, you can enter the data that is relevant to that question. And if you've got different nanomaterials that you're considering as part of a panel, you can see how they compare. It allows you to see if there's any gaps in your data for these IATAs by populating these matrices. Alongside each of the decision nodes in the IATA, we have tiered testing strategies. So this just means that we've organized our testing into different phases. So the earliest phase or tier is using really simple models. So it could be acellular tests. We're using simple in vitro models. And here I'm focusing on human health. We've also developed them for environmental settings. There's also more complex models as part of the second tier that could be, co-cultures or in vitro cultures. And then ultimately you could test in a rodent, but this wouldn't always be required. When they're available, we do recommend standard methods, but currently we don't always have standard methods available for all the responses we want to investigate. So again, this looks quite complicated, but it's just to emphasize to you that you don't need to complete every single tier of testing to make a grouping decision. And this is where the purpose of grouping becomes quite important. So if you were performing grouping for safety by design, you wouldn't go to the complex higher tiers of testing. You would maybe rely on the lower tiers of testing that would not require animal use. There's more uncertainty associated with your grouping decision, but it means that you can avoid performing animal testing. You'll also see here within the testing strategies also emphasizes reviewing the existing literature. So we're trying to encourage people not to do testing if there's already information available that can be used to make a grouping decision. So here's some activities for you. We're going to start. So we have an oral IATA presented on the slide. So it's saying that nanoform is showing partial dissolution, that following oral exposure, both the nanoform and its constituent ions or molecules will lead to local inflammation in the gastrointestinal tract. So what do you think we would need to ask as part of our IATAs? What questions might we include to try and identify if we could accept or reject this grouping hypothesis? So I'll go back to Menti and present this. So if you prefer, you can write on the slide, and I realize it might take you a few minutes to do this. You should be able to see the grouping hypothesis when you look online on Menti, but just think, what would you need to know? What questions would you ask? And feel free to talk to each other as well, or if you want us to come over and speak to you as well. We'll give you a few minutes because it will take you a while to type, I think.
Maybe we announce once again what the scenario was.
Can you see the grouping hypothesis when you look on Menti? Is it? Yeah, so we can't see it here, but I think we can see it. Oh, here we go. Yep. So asking about solubility and what the dissolution rate of the nanoform is, what it's made from. So concentration, do we mean how much we're exposed to this substance? Don't know, I can't always tell. You wrote this, but yep, so you can see this grouping hypothesis is centered around dissolution, right? So one of the questions you need to ask is, what is the solubility? So this is captured in these points here. So solubility in what? In what type of media would you look, or what type of situation? I'll give you a few minutes to think about that.
What else would be interesting? Not only they look for the chemical composition or the solution rate, what information is very what to make it be a cross-border.
Yeah, so you could assess solubility in media that's relevant to gastrointestinal fluid. Yeah, you can look at its lipophilicity. I can never say this word. No, it's lipid liking properties. Hydrophobic, hydrophilic. Yeah, the size of the particles can be useful. So what we're going to do with this one, this is to get you thinking. I'll show you the IATA and then we'll work on another one so that you can learn what we've applied for this one. But these are all really relevant points. They're all quite focused on dissolution, I would say. So look at the hypothesis again and look and see what are the different elements to it. Dissolution is one, but there's also other important features that you might want to see if you can pick out. Yeah, they're able to cross the barrier. So now we're getting onto more biological endpoints, I would say. So that's really important, that you want to consider what cells are being exposed in the gastrointestinal tract. How are they responding? You know, the hypothesis specifically mentions inflammation. for example. So you need to consider, are you going to ask questions about that within the IATA? Sorry, this changes so frequently. It's difficult to keep up with it. Yep, so we've mentioned the types of cells here. So we have some really good suggestions. Things like uptake, are they interacting with the cells? So what I'll do is I'll come out of this presentation. We'll go back to the grouping presentation and I'll show you what we consider, and then we'll apply what we've just learned into another example. So this looks super, super complicated. So we're going to go through it bit by bit. But essentially what we actually have is a number of different grouping hypotheses that have been merged into a kind of super IATA, if you like. So don't look at the detail just now, just look at the different components. So the first part of the IATA actually asked, is there oral exposure? Because if there's not, you can't consider this grouping hypothesis as being relevant to your nanomaterial that you're interested in. So this is a common theme, I would say, for all the IATAs. The first thing is asking about exposure. Will you get an oral exposure? Because you can see that was really important to the hypothesis. Next, we're asking about dissolution. So you all mentioned, or some of you mentioned this dissolution in gastrointestinal fluids, but it's also asking about dissolution in cells as well. So there's two different components to that assessment, and then ultimately you look at the hazard. So if we look at some of the detail of the IATA now, you can see here that we often provide cutoffs, if you like. So you can see that we've mentioned partial dissolution, instantaneously dissolving, very slowly dissolving. So it's important to help guide people so that they understand what we mean by those different terms. So you can see that, you know, times are related, or the dissolution rate is provided here, or half-life. So we're trying to find cutoffs. This isn't always possible when we're making these IATAs. We don't always have the information that allows us to introduce those cutoffs or thresholds, but it allows you to identify group members more easily if you can establish these cutoffs. So the first part of the IATA is saying, what is the dissolution rate? And that allows you to say if it's instantly dissolving, partially, you know, very slowly. And then represented in these figures is that if something instantaneously dissolves, it's the ions that are likely to be driving the toxicity. Whereas if it's very slowly dissolving, it's likely to be a particle-mediated effect. And then in between this, you probably have a mixture of ions and particles contributing to that toxic response. So it's just to show you that you can have these different groups of nanomaterials forming. Next is very similar, but this time it's asking about lysosomal fluid. So it's more of a cellular response we're looking for in dissolution there. And again, you can see that we have these cutoffs provided. So once you have that information on dissolution, you start to look at hazard. So again, there's a lot of information here. Please don't worry about looking at the detail, but this part of the IATA looks at hazard-related questions. So you can see it's saying, is it cytotoxic? Is it inducing an inflammatory response? Is it genotoxic? So it's combining that information on exposure, fate, hazard. Yep.
So now you have all this. Would you ever have particles? So when you put up all this, would you ever have chemicals slash particles slash nanoparticles that can be used? I mean, this is a lot of different colors. Some of the things that we have to align on. A lot of guesses go down before you guess.
Yeah, so that's the thing.
Eventually.
Oh, yeah.
If it's possible.
So a question in the room is that will it actually be possible to group nanomaterials? Because there's so many questions that you have to answer yes to, that will you actually get a situation where that is true? So we'll show you an example of that later, where you can apply these IATAs and identify different groups of nanomaterials. So hopefully it'll be clearer when we show you these case studies where we take nanomaterials that have different properties, put them through the IATAs and see what conclusions we make. So it is possible, but you do have to gather a lot of information to make these grouping decisions. But don't forget, some of it could be a tier 1 test. So it could be relatively quick and simple tests that you make or that you perform to make a grouping decision. But we will go into that later. But yeah, it's not a simple one question, yes or no. It's quite a lot of steps in the process. think Eric has a question or comment.
Or comment more of an addiction. I think clearly the nanomaterials is difficult now, but I think at the beginning we have to use us for chemicals, but that also took us 15 years to come up with something useful. So you really need a lot of data to finally say, okay, I know my block KOW, I know where that goes within the living environment. So it takes time. For the nanomaterials, we're still at the beginning, but yeah. Each step that, and as I haven't mentioned, for small groups, we can do, and the group will grow while we move on.
So again, there's a huge amount of information available on this slide. I don't expect you to read it, but I'll give you a basic overview of what's presented. So I mentioned these tiered testing strategies. So each of these columns represents one of those decision nodes within the IATA. So it's just about showing that each decision nodes have these tiered testing strategies, and they progress from, it can be physical chemical characterization of the materials, acellular tests, really simple in vitro models. And then as you progress through the testing, you start to use more complex models. So it could be 3D co-culture models, and ultimately rodents. So each of these decision nodes that we've mentioned does provide or have a tailored testing strategy that allows you to gather that information. So we're hoping that people gather the information in a consistent way. So that was our practice one. Do you want to say something?
I may ask something, because this tiered approach is also something complicated. There are more simple assays, and then this tier 1 is sufficient. And then there are more complex assays that you can exclude. How do you, is there a kind of a procedure or something where, or kind of an advice where you learn how many of these simple cases would be enough, or when do I need in addition the advanced or the tier 2?
Yeah.
To differentiate between.
So it probably depends on the purpose of why you're performing grouping in the first place, because for, let's say you're doing safer by design, you probably wouldn't do an in vivo study in the first instance. You would start with these more simple tests. For regulatory requirements, you may have to perform an in vivo test. So we would always recommend that you avoid animal testing where possible, and that you work your way through the tiers. So you wouldn't start with an in vivo test, that you progress from the more simple to more complex. But,
yeah, but there are these more complex, and I guess complex in vitro models also are in the tier 2 already, right?
Yes. And so there's more uncertainty, I guess, with the earlier tiers. If you make a grouping decision using only tier 1 testing, but more uncertain about, there's more uncertainty associated with that decision. If you performed in vivo testing, you would perhaps be more confident in your grouping decision, but not essential to perform all tiers. Okay. Okay, so we'll move on to another example now. So this example relates to high aspect ratio nanomaterials, so things like carbon nanotubes, for example. And just as a bit of background, that we know that following inhalation, then certain forms of asbestos fibers can cause adverse health impacts like mesothelioma. So we know that there's a structural resemblance to some harm to these pathogenic fibers. So we want to identify which of these harm may cause a similar hazard to asbestos fibers. So we know from existing information in the published literature that things like fiber width, length, rigidity, and biopersistence are all very important to the pathogenicity of fibers. So we've used this existing information to feed into the development of a grouping hypothesis and the formulation or design of these IATAs. So the grouping hypothesis that we formulated, or one of them, for high aspect ratio nanomaterials is that respirable, biopersistent, rigid harm, that following inhalation, they will translocate to the pleura, so a particular cavity within the lungs, and mesothelioma development can occur. So it tells you here about what properties the materials will have, what their fate is, and then what the hazard may be. So like we did before, I just have to go back to Menti. Can we think about what you might consider within an IATA? So it'll just take me a minute to... this one. So again, you feel free if you're in the room to get the microphone and speak, but you can also use Menti. So what questions would you ask? So learn from what we've discussed from the oral IATA and use that thinking again to suggest what you might ask as part of a grouping or as part of an IATA for the Harn grouping hypothesis. So again, hopefully you can see it on your Menti page. If you want me to show you the grouping hypothesis again, please let me know. Oh. Yes, so biopersistence would be key to this IATA. Yep, exposure. So you want to check what is exposed, what system. Yep, size, so diameter of the fibers. We know this is important to their pathogenicity. Yep, are they bent? So we mentioned rigidity within the hypothesis this time. So that's come up here. So these are all really good examples. Yep, cellular interaction. So I didn't speak to you about what exactly these fibers will do in the lungs, but you want to know what the consequences from a hazard perspective. Anything else? So we have exposure in the lungs, but where do they need to go? It's not just the lungs, right? So it's quite specific in the hypothesis about exactly what the fate of these materials should be.
Like one word is also important one. I have noticed little two groups described it because we have so the quantity here.
Yeah, there's one important thing here but missing actually. Yep, so we have size, so we mean diameter of the fibers, but also the length. Someone mentioned something important here that I've just moved. Yeah, mesothelium. So we want to know, does it cause this lung tumor that is associated with pathogenic fibers? So yeah, transport. So again, this can be the fate in the lungs. I'm assuming that you mean where in the lungs are they accumulating? So yeah, these are all, yeah, aspect ratio, perfect. I think this is the one that was maybe missing, but probably of greatest importance to this this hypothesis. Okay, excellent. So what I'll do is I'll go back to the presentation.
I'd like to suggest to add a physical concentration for many of these fibers. So persistence in the balance from which.
Yes. So within the decision, so just in case you couldn't hear at home, so there's a question relating to providing information, for example, on what the critical concentration was, what is the biopersistence. So that comes out within the testing strategies almost. It'll have guidance on what the properties are, more specifically, what the hazard is. Yeah, there's another question.
I think the funny thing is with this harm hypothesis is that initially actually only one harm located in the stomata can cause this. So yeah.
Yeah, so that's the thing. We don't say that it has to be. In fact, Fiona, you can correct me if I'm wrong, but in terms of exposure, I don't think that the IATA currently considers a threshold for exposure.
No, in terms of, we don't have a set limit for the deposition level in the lung, and this is largely because we know that there's no lower limit to asbestos exposure that's linked with mesothelioma development. So you can be exposed to a very few number of fibers and develop mesothelioma. So we didn't want to set a lower cutoff.
Fiona is the person who developed these hypotheses in IATA, so she's attending virtually from Edinburgh, just so you all wonder who that was. Okay, so this, I don't know how much of the detail you can see in the room here, but again, it's quite similar to what we saw previously, that the first question you ask is, will you expect inhalation? Because if you don't, then this hypothesis is not relevant at all. Then you ask, does it deposit in the distal lung? It's asking about dissolution in lung lining fluid, so it's coming back to this biopersistence that was just mentioned. So ask about lung lining fluid, but also in phagolysosomal fluid, because macrophages are expected to interact with these materials after exposure and could help with their degradation. Then it's asking about translocation to the pleural cavity. It's asking about the length, and here you can see a cutoff is provided. It's asking about the morphology of the materials. Are they fibrous, rigid, with a needle-like morphology? Do they cause something called frustrated phagocytosis? So the longer the carbon nanotube or the harn is, it becomes increasingly difficult for macrophages to internalize them, and that's a really important part of their pathogenicity. So you can see that there's, again, quite a few questions that we have to work through, and this is the IATA will come back to with actual real-life examples of carbon nanotubes that we have posed these questions about. So the other thing I want you to think about, because we've discussed it in a little bit of detail, is how would you assess this? So if you were to design a tiered testing strategy, so in reality, each decision node has a tiered testing strategy, but just think about maybe more generally, what kind of, sorry about this, what models might you use? Oh, I pressed the wrong button. Apologies. Here we go. Hopefully you can see that now. So have a think. We've talked about properties of the fibers. How might you assess them? How would you assess these hazard responses? What models would you use for that? So just take a few minutes to think about what kind of elements you could include in a testing strategy. And again, in the room, if you feel free to shout out answers or speak amongst yourselves, or include them in Menti. Yep, so we have lung model. So by this, perhaps we mean an in vitro model.
Also the in silico modeling for the second question, this reaches the distal lung.
Yeah, so in silico model, you know, when we're looking at deposition of nanomaterials, there's in silico approaches. Sometimes they're not always applicable to fibers because they've been developed for spherical particles, but certainly if there was modeling that could be done to predict deposition. So pleural injection would relate to in vivo models. Yep, so we have an example on the slide here that wouldn't require, you know, in vitro or in vivo testing. It's an acellular test, so you're looking at dissolution in a lung lining fluid. Yeah, you could look at reactive oxygen species generation. So I don't know if this means by cells or by, or to assess the reactivity of the harn. Yep, so electron microscopy for looking at size and shape, using macrophages. Accumulation, so yes, something to look at the fate. So you can see there's quite a lot of diversity in the types of approaches that you could employ, and we're looking at different endpoints. We have things related to the properties of the harn, but also related to the fate and toxicity here. Yep, DNA damage, so you could look at genotoxicity. And a phagocytosis assay. So yeah, so we did mention specifically frustrated phagocytosis within this IATA, so we need a test to assess that. So these are all really good suggestions, and what we'll do within the next presentation, the case studies, I'll show you what we've done to test this hypothesis. So just move on. So this I'm not going to go into. So the thing I want to just mention again briefly is read across. So the whole point of making our group of nanomaterials is so that we can perform read across, so that if our nanomaterial lacks data, then we can use existing data for a data-rich substance. So there's also a lot of guidance on how to perform read across, but you do need to provide quite a robust justification of that your nanomaterial is similar to this source material for which there's a lot of information. So just to emphasize this, and we can perform something called similarity assessments. It's not something I'm going to dwell on now, but Mario will cover it in a little bit of detail, but that's using approaches to assess whether or not there's similarity between different nanomaterials to help with grouping, but also to help with this read across argument. So we're running out of time a little bit for this part of the presentation, but just to let you know, we have things like a blueprint that can be incorporated into software. So a lot of the information in the framework can be integrated into risk assessment software, and there is guidance documents available. Now we're at the stage where we're trying to adapt the framework to make it suitable for informing the safer design of future generations of nanomaterials. So this is being done in the Sunshine project. It's about kind of a year and a half into this project now. And we are modifying the grouping hypotheses, we're modifying IATAs, and it's to make them more suitable for assessing the toxicity of more advanced nanomaterials. So the nanomaterials that were being considered in the grouping hypotheses previously were relatively simple in comparison. Now we have these much more advanced multi-component structures. So just in the interest of time, I'm going to come out of this presentation and go into this one, as it'll help with one of the questions earlier. Is there any questions before I move on to this case study? I know it's quite complex.
I have this question, when you do application of school, are we talking only about like new nanomaterial or
Yeah, so I mean, grouping is relevant to any material. So we're focusing on nanomaterial, but the approach that we've used could be used for any chemical substance. For any chemical, for any particle, you would still need a hypothesis-driven approach. So what the framework we've developed could be used for any chemical substance, any material. Mm-hmm. Mm-hmm. Yeah. Yeah. So just in case people at home can't hear, I guess the question is the applicability of the framework to things that are not engineered nanomaterials, to other particles, to other chemicals. Then the second part was what happens if there's no information on a chemical, a material that you're interested in. So we do encourage people to use the hypothesis template to formulate their own hypotheses. So the hypotheses we've developed aren't going to be relevant to every single material or chemical. So we give advice on how to formulate a grouping hypothesis. You can generate your own bespoke one and then test that. But you'd need to generate an IATA alongside it as well. So it's not a simple process. And, you know, we're in these ongoing projects, we are developing more hypotheses, making them more suitable to a more diverse array of materials. Yep, there's a question at the front.
I'm just thinking, when you create these hypotheses, you need to narrow them down in some way, because if you just make the hypothesis, does it cause wrong information?
Yeah.
Then it will be impossible to not miss something, or yeah, there's too many variables. You also have to cut it down, I guess.
So that's the thing, they can't be too, so I guess the question is answering how specific you make the hypothesis, because it can't be too broad, because then everything would be in the same group. So it does have to be quite specific. And so we do require particular properties. And you see, it's not just related to one physical chemical property, it could be several, and to the fate and to the hazard. So it's not just, it's not a simple process.
So I guess, do we have something like 42 hypotheses?
Yeah, there's around 40 at the moment. So I think each human exposure route has about 3 or 4. And then the rest are environmental, split up into aquatic and sediment soil compartments. So, and to be honest, most of them currently are focused on dissolution, apart from the harm, the harm hypothesis is slightly different, but there's a big focus on the dissolution of the nanomaterials. Just in the interest of time, we'll move on. Just to show you about how it actually works, because what I've showed you now is quite theoretical, and it's difficult maybe to imagine what would happen if you actually had a material that you wanted to test. So Fiona, who you've heard virtually, is actually been the person that's been leading this and performing a case study. So essentially, she worked with a panel of different multi-walled carbon nanotubes and wanted to identify if she could form an evidence-based group. So there's several different purposes to performing this case study. And the first was just to see, could we group these carbon nanotubes based on their common fate or hazard? Could we identify data-rich members? Because this is really important to read across. If we could identify members of the group that there's a lot of information for, these could be used in the future as source materials. And then lastly, it was to determine if the multi-walled carbon nanotubes that lack data, if we could read across from existing source material. So I'm not showing you everything in this, I'm just going to show you a little bit. But the approach that was used is that we had 15 different multi-walled carbon nanotubes. So we focused on studies that were published by the NRCWE in Denmark. So there was quite a few published articles available on these materials. So the first stage was to extract information on the materials to determine if we could accept or reject the grouping hypothesis. And then the second stage was to fill any gaps. So either look to a wider literature data set or to perform new testing. So as I mentioned, the first stage of using the framework is to identify what grouping hypothesis is relevant. So inhalation would be regarded as the most relevant route of exposure for multi-walled carbon nanotubes. We actually have 6 hypotheses that are relevant to inhalation. I mentioned previously that you have to provide this information on the characteristics of the materials and the fact that they all had a high aspect ratio. So this represents the code names of all the materials that were tested. They all had a high aspect ratio, so this led us to test the Harn grouping hypothesis. I'm not going to go into this detail, but remember it's that they're biopersistent Harn that deposit in the distal lung and accumulate there are likely to pose an asbestos-like hazard after inhalation. So this is the grouping hypothesis that we're focusing on. We spoke about this IATA previously, where we're looking at the fate, the properties of the materials and their hazard within the IATA, within each of the decision nodes. And we have our tiered testing strategy. So this informs what tests should have been performed to gather the information for each of these decision nodes. So within the first step of the case study, we only relied on tier 1 information. Someone mentioned how much information you need to use to make a grouping decision. So first, we just focused on tier 1 tests to identify if this was sufficient. So again, there's a huge amount of information on the slide. Don't necessarily want to detail, but this is, each slide now will represent a decision node. So this is saying, can Harn deposit in the lung? And it's telling you how to assess that response is associated with the decision node and what the criteria is. So for this one, the aerodynamic diameter of the Harn needs to be less than 4 microns. And you can see here that we have values for each of the materials here. And this is our decision on the right-hand side here. So we have our panel of materials, and it's asking about just deposition in the lung, and it's saying that we have an uncertainty around this data. So essentially, all of the materials had a diameter below the cutoff, but there was a lot of uncertainty associated with the data that was used. So you would feel more confident in answering this decision node if you progress to a higher tier of testing. The next question was asking about the length of the harn. So remember, their length is really important to their pathogenicity. So again, it's saying you need to make measurements using electron microscopy, and it gives you a kind of threshold, a cutoff. It's saying that at least 10% of the materials need to be greater than 5 microns in length. So here, for each of the materials, again, we have the data provided. But unfortunately, although we had a mean length for each of the samples, we didn't have a length distribution, so it made it difficult to answer this question that was posed in the decision node. So we didn't have the data available to answer yes or no based on the literature that we were looking at. The next question asks about the rigidity of the harn. Are they fibrous? You know, what's their morphology? Again, we have recommendations on how to make those measurements, and we have a cutoff again about what their diameter should be, and that you need some electron microscopy images to make a decision. So I've highlighted the two materials here, NM401 and NRCW006, because they met the criteria at this time. We could answer yes to this decision node. For the rest of the materials in the panel, we answered no because they didn't meet the criteria. So for this decision node in IATA, we can answer yes for 2 of our materials, but no for the rest. And you know, we have quantitative data and also qualitative data here from the images. You can also see that there's some information here on tier 3 testing, just because we had that available to us for some of the materials. So it allowed us to confirm for these materials that we answered yes at tier 1, that the same was also true for tier 3 testing. The next question asks, does the nanoform cause frustrated phagocytosis? Again, it recommends an in vitro assay looking at inflammasome activation for tier 1 testing, but there was no data available in the literature. There was, however, some data available from in vivo studies that could be used to establish the answer to this decision node in the IATA, but we didn't have data for all the materials that we were considering as part of this case study. So I have a question for you. So we have 2 materials here that I've highlighted. The first one, the top row, is NM400, and you can see that we have sometimes answered yes to some decision nodes in for this material, and often no. And then the second one, where we have information available, we've answered yes. So we won't use Menti today. We can just maybe put our hands up. For this NM400, do you think we should accept, reject, or gather more data to make a grouping decision? What would your instincts be? So these all represent different decision nodes. We have a couple of yeses and we have quite a few nos. Would you feel confident saying yes, or we should accept this grouping hypothesis, or no? Or are you unsure? I think there's a lot of uncertainty. How about the other one where we have quite a few yeses? Would you want to accept the grouping hypothesis for this material where we have not information available for all decision nodes, but we have quite a few yeses?
And please repeat that, because we cannot see exactly the title of each column.
Okay, so each column represents a different decision node, and then we have tier 1 testing, tier 2, and tier 3. So for each decision node.
Yes, so for example, the yes is in which decision mode?
So it's the one on the top here. So this one says, does the nanoform dissolve? So if you're answering yes, you're saying it dissolves slowly. So it's saying it's biopersistent. So essentially, if you answer no to any decision node, you reject the hypothesis. There's no way that you can probably change your mind and accept it. So it doesn't matter the level of testing or tiered testing that you have. You have no to some decision nodes, so you're going to answer no. For the ones where you have yes, you might be tempted to answer yes and accept your grouping hypothesis and form your group. However, you have gaps or you have uncertainty. So this is where more information would be required to make that grouping decision. So if you have a no at any stage, you reject. If you have yes, you would need it for every decision node. So you need to gather more information. So that would be the outcome of this part of the case study, that for the ones that you have no, you reject and you don't consider them further. But the ones where we have yes, answer to quite a few decision nodes, we would actually want to do more of an in-depth investigation and gather more information so we could be more confident in accepting our grouping hypothesis. So I'm not going to go through this in a lot of detail just because of time, but what we did next was do a much more extensive literature search. So the materials that we were focusing on the case study, 2 of them looked like we could accept the grouping hypothesis, but we wanted more information to be more confident in that grouping decision. So we looked at each of the decision nodes again, and based on tier 2 or tier 3 testing, we looked to see could we answer yes to these decision nodes. And actually we could for most of the decision nodes. So this here shows you that more extensive tests were done in vivo and that we had more information on the deposition of these particles, harm. So it allowed us to answer yes for this decision node. The same was true for the biopersistence related question. Again, looking into the literature more, we had much more evidence for these materials that they were biopersistent. The same was true for the length, that we were able to gather more information. We did perform some new experimental work to help address some of the decision nodes within IATA, and that allowed us again to become more confident in confirming that they cause frustrated phagocytosis. So in the end, what we have is a situation where we have these 2 materials, and now for each of the decision nodes, not in all tiers, but at least for the majority of the tiers of testing, you can answer yes. You would be much more confident in accepting the grouping hypothesis under these circumstances. Does that make sense? So out of the 15 materials that we had, we could only accept the hypothesis for 2 of them. So those would be group members, you would accept it. For the other ones, it doesn't mean the framework is no longer helpful. You would then go and maybe look more generally at the other inhalation grouping hypotheses that we have. So I'm going to end here just because we do have another presentation. I'm sorry it was quite a lot of information to take in a short amount of time, but hopefully it shows you the usefulness of grouping with some kind of practical examples. And Mario is going to go into a bit more detail on, from a regulatory perspective, about how we could actually use grouping to a greater extent. So if I just...
Maybe a short question is also this accessibility to this area. I mean, it needs to be somehow evidence-based, right? So determination, ways to determine basically whether they can really reach this area, whether just a single one even reaches. And also needs to be differentiated for the human and the mouse system, because you compare the pears to the apples, the mice to the humans, right?
Yep. So
how about that?
Yeah, I mean, the grouping hypotheses, IATAs, are all published, and now we're starting to publish more on the case studies. So industry have been participating in the case studies. I think Mario is going to give you more specific examples now, but it's to show you that they are useful, that they are able to help grouping. But yeah, the evidence that you need to support that grouping decision needs to be really robust, and you need to be able to
robust means kind of accepted essays for such type of lung deposition in this way.
Yeah.
In this case.
Yeah, also good day from my side. What I will do on my talk, I will, as such, follow up from what Eleanor has already presented, and also what Fiona has compiled together and tested with this Hahn Yatta.
So the first slides I will jump over because it was already mentioned. Here, just one word or some words why we do grouping. So the point is, when a manufacturer is registering its chemicals in ECHA for marketing, so that it can, or that the manufacturer or importer can sell the chemical on the market, they have to provide a lot of information actually. And here you have just an overview what information actually has to be provided. And this is tonnage triggered. So which means in the lowest category of 1 ton or more, the tests which have to be conducted would be based on sensitization, for example. But when a higher tonnage level is automatically triggered, like 10 tons, 100 tons, or even 1,000 tons and more, then all these tests together have to be provided by a manufacturer. And but just by the number of tests or information which have to be provided in the end. So it is a huge amount of money which have to be put into this testing, and therefore grouping is one of the most common approach which is actually used to fill these data gaps in regulatory dossiers for the marketing then in the end of a chemical or a substance. So, but when we look into the REACH regulation and we want to see, what is there described for grouping of nanomaterials, we have actually two cases which we have to differentiate. So on one side, when we look into the regulatory texts, is that we can form so-called sets of similar nanoforms, which means that these nanomaterials are only allowed to have slight variations within a very narrow boundary. So it means they are all very close in their characterizers, which means size distribution, surface area, also the surface functionalization has to be almost identical, and only then we can form these sets of similar nanoforms. And the important point here is also to mention that within a set, risk assessment can be performed jointly, which means for the testing, I can take one of this material from the set and test it with all the tests which have to be provided to get this information, to have this standard information obligations fulfilled. And then this whole information set is valid for the whole set of similar nanoforms. The other option, which is described, is so-called endpoint-specific grouping, which means this grouping is performed for toxicity evaluation. This is actually the case what was described by Eleanor. So here I do this grouping to perform a read across for one specific endpoint. For example, it can be acute toxicity, subchronic toxicity, skin sensitization, or genotoxicity. But here also special cases are coming, because I can do this endpoint specific grouping even between sets of nanoforms, but not vice versa. So now to come to this kind of exercise and why we were thinking to bring this kind of grouping or the regulatory side also in the hands-on training. And here I will focus just right now, because in the constraint of times, on the right-hand side, this tangled multi-oil carbon nanotubes. And the reason is, for these tangled multi-oil carbon nanotubes, there are not so many informations to already rule out some concerns which were identified. And to get a better understanding and maybe to see what information is actually available for this tangled multi-oil carbon nanotubes, we performed a so-called substance evaluation, which is conducted to clarify whether their use pose a risk to the human health. And the specialty is, during the substance evaluation, it's possible to request additional information from the manufacturers, which can even go beyond the standard information which they have to provide for the material. So if we have a concern and we can justify that the concern might exist, we can ask tests which are usually not necessary to provide according to their annual production. And what we have seen during the substance evaluation was even that the registrants have tried to apply grouping and read-across approaches to avoid additional testing for their materials. But we have identified a number of issues with the type of grouping what they have actually applied. And to give you an overview what issues were observed, I included here this slide. So the first of all, what we have seen was that the groups were not well justified. So the manufacturers have tried to combine materials with different impurity profiles, for example. Also, they have tried to combine materials to a group which showed different morphologies or higher ordered structures were present, so-called aligned bundles of singlet tubes. How or what you can imagine out of it, it's shown in the pictograms below. Here in the middle is, for example, a scheme how this aligned bundle can look like. And even on the right-hand side, you can see how a TEM image of these bundles will look. And the specialty is actually, or what we have to consider here is that if even a single fiber would not, or would be very thin and can entangle, these larger, highly ordered aligned bundle structures meet the WHO criteria. So there is the concern that they might show the fiber toxicity, that they fulfill the fiber paradigm. And therefore, for us, it was a kind of question, actually, can these materials be grouped together or not? And to assess or to see if we can group these materials together or not, as a follow-up activity to the substance evaluation, we performed a grouping case study where we actually tried where we asked Gracious if it's possible for us to take their Hahn-Yatta, what Eleanor has presented, and to test if this is applicable in our regulatory context. So the basic question was, can these materials group together because of these aligned bundles and single fibers which were present? The good part was, or the nice part was, we had even a larger data set. So overall, we had 39 carbon nanotubes in our data pool, which we could consider. And we wanted to see in the end if we can identify endpoint-wise grouping possibilities out of this data sets, but also we wanted to see for the regulatory side, what are the chances and limitations of the developed grouping framework by Gracious. So, and what we tested actually was, what we intended to test were 3 different predefined hypotheses. Here, I will just present the outcome of the first hypothesis, and this is the same as Eleanor has given in her example. So we looked whether these multiple carbon nanotubes are rigid, respirable, high aspect ratio nanomaterials. So they are long, persistent fibers, and once inhaled, they cause frustrated phagocytosis, lung fibrosis, and maybe tumor development. And at the bottom is shown, so overall in the registration dossiers, we have seen 51 nanoforms were mentioned, 39 nanoforms actually had sufficient data, which we could consider for the case study. 11 of them actually were also noted by the manufacturers that they are aligned bundles or that they appear in this aligned bundle shape. And for 6 of them, we also had, overall 6 of them, we had repeated dose toxicity data. So we had in vivo inhalation data for these materials. And with this, we started to see whether this Hahn-Yatta is applicable in our case or not. So I will not go to all the details, what was the readout or what was the dimension, because it's confidential data as it was coming from the registration side. But here I have given you the overview, what was the outcome of this testing of this Hahn-Yatta. The result here is color-coded. Green means that the parameters by these materials comply with the underlying question of the decision node. Red means they don't comply. And what we can see is that for the lung deposition, for the dissolution or biopersistency, and for the length, all of the fibers, all of the CNTs which were present in the case study complied with the defined thresholds or values or selection criteria developed by Gracious. And the first diverging results, actually, this we observed when it comes to the question, is the Hahn rigid and maintain fibrous morphology? And here, actually, the point was that let's say cutoff criteria was that the fiber should be larger in diameter than 30 nanometers. But of course, as we are looking for tangled materials, the reason was here that the fibers were actually smaller in diameter. So that is the reason why we don't comply with this outcome of the Hahn-Yatta. But as I mentioned, when it comes to these aligned bundled structures, here, of course, when we see the dimensions for them, they all still comply with this criteria. So means they're all larger than 30 nanometers and would fulfill this categorization as a Hahn material in the end. So here we had a kind of diverging result, but nevertheless, we continued with the assessment of the materials, and we looked also for the toxicity side. So with the 6 toxicity studies which we had, and along this MWNT7 as a reference material, we looked how does this materials show the toxicity. Is there some comparability between the toxicity profiles of the materials or not? And here we compared the outcome of this 90 days repeated dose toxicity inhalation studies. And the question was, does the nanoforms show a similar inflammatory response? What you can see here on this graph, it's a quite complex graph. On the top, you see the different exposure concentrations which were applied. On the left-hand side, you can see the different materials. CNT1 and CNT2 actually was used to describe the toxicity of the same registered material. The both opt-out materials actually tried to test this aligned bundle materials. And what we can see is, in general, by the bars, that we have a very high heterogeneity in the inflammatory response of these materials. So overall, we have seen that we have high variations, and because of these variations, we have a limited representativeness actually of the studies, so that we cannot finally say whether we have a unique mode of action which allows to categorize them as a Hahn material or not. We also have identified a number of uncertainties. For example, we have seen that the individual materials were treated differently to prepare an inhalable aerosol for the in vivo exposure. Different techniques were applied for deagglomeration of the materials, and also in some cases the materials were grinded so that they comply with the actual OECD guideline which is underlined. So the question was then, how can we reduce this uncertainty? And for this, actually, Gracious has provided a number of solutions. And what Helena also asked you before in this Mentimeter, what endpoints can be assessed on top? And the idea would be maybe we could do, or the manufacturer could do an assessment of frustrated phagocytosis, or look in vitro, or maybe more complex co-culture experiments for the inflammatory potency to have some additional information. But what is important here to point out, this tier 1 and tier 2 tests, which are suggested by Gracious, the question is behind, are these tests actually regulatory valid for grouping? So for the regulatory side, the gold standard right now is still to have in vivo experimentation, and we are just at the beginning to see whether these new approach methodologies, these alternatives to animal experiments, they can provide the sufficient information to replace them and to become regulatory important or relevant in this context. But now we have seen, okay, our materials, or the majority of the materials, when we look for the single fibers, they don't comply, but maybe we can look between them, how similar are these materials? And this is also what we have tried in our case study. So we wanted to see, or can we demonstrate similarity? And from the research side, to look for similarities or to have a kind of grouping, like principal component analysis as a method is applied. So you have different algorithms, and we have looked at different of these algorithms, like X-fold differences, Euclidean distance, or even cluster analysis, to see how these materials relate to each other. And from this, there's also then planned for you a slide exercise, a very easy exercise to see, or to get your opinion on these materials. So, and what we thought of was maybe to go for a pairwise comparison that can be conducted, and where I would like from your side to have an idea what you think, what this result or how this result could be interpreted. But before it comes to this, we also have to look for some terminology which we have to consider. So here you have just a kind of definition which we applied. So we have on one side a property. A property can be a reactivity, attachment efficiency, for example. It can be also size, surface area, or shape. So in our case, for this example, we will look for the diameter of the fibers. Then we used so-called scalar descriptors, so which means we have looked for the D50 values, which we have taken for this pairwise comparison. And based on this, we have created a data matrix. And actually, what to imagine from the outlook and what, how this data matrix look like and what we have done. So here you have this pairwise comparison. You have CNT1 compared to CNT2 in the diameter, and you fill up this data matrix with the color coding as it's shown. In the data matrix, which comes on the next slide, red color means there's a dissimilarity, a green color means there's a similarity. And this actually you do by comparing all materials to each other, and you get this matrix in the end. And this was actually the outcome. So you can see here, this color-coded outcome, you have green and red color coding. And for me now, it would be a question to you. What do you think, what could this mean? And what you would conclude out of this data matrix based on this assessment of pairwise comparison of the fiber diameter. So maybe you can discuss it with your neighbor. Also, maybe you have some ideas directly, so please speak up. I give you, let's say, 2-3 minutes, I guess we have time.
Yeah, we are actually.
Okay, yeah. So maybe 1-2 minutes. Anyone has an idea? So what can we make out of this result?
The red one is Mitsui 7?
No, Mitsui 7 was actually not included. But it's a good thought actually. But Mitsui 7, our reference, we have not included. Some other idea. Okay, yeah, I don't want to hold you back. Oh, one question?
Couldn't conclude anything because these, as far as I understand them, I'm not a toxicology expert, of course, but I can see only dimensional or morphological similarities between the nanoforms.
Exactly.
How do you attempt to conclude which one it could be harmful or not?
So
these some other parameters like chemical composition or aspect ratio that are other elements to be determining PSR.
Yeah, of course, you're right. So for the similarity assessment, we have to look for more descriptors, for more properties, not only for the diameter, but the diameter here was chosen as a easy example. And because even we have this very nice result that actually one material stands out compared to the rest. And to make it short, so this material which stands out was labeled CNT18. And on the right-hand side, you can see in table with the diameters. So it's not the actual diameters because of the confidentiality reason. But what stands out here is usually, or there is an average level, we have some diameters between 10, 15 to 20 nanometers. But for this CNT18, actually, it was much larger, much wider in diameter compared to the rest. And just as an anecdote for you, even recently we heard back, or it was back communicated to us, that the manufacturer who had put this material in the registration dossiers had retracted it because it was actually, not a tangled material, but a rigid one, and was falsely put into this registration behind it. Yeah, the last 2 slides which I have is actually the conclusion from the Hahn-Yatta. So what we could see is for the tangled material which we tested, fiber-like pathogenicity was not obvious, but as such, the Yatta has worked. So the Yatta was intended for rigid materials, which should cause lung tumor formation, mesothelioma formation. In our case, it has worked because we were focusing on these tangled materials, but we've also seen a number of uncertainties like progression and reversibility. So from the toxicity data which we had, not all were considering afterwards the recovery period, for example, long-term inhalation studies. So what is also maybe necessary when it comes to tumor formation. So 2 years in vivo study were not available. And a big question is how to address this aligned bundled structures or phenotype, which we have also observed, because they comply with the WHO criteria. So they might show this specific fiber paradigm or fiber toxicity, while this tangled materials actually might show a different mode of action, which still needs to be elaborated on. And what we have learned also, just to make it short, so also what you mentioned, rigidity assessment is a very critical point. The problem is from the regulatory side, there is no validated method actually available how to assess rigidity currently. Also, what we have communicated with Gracious was already this definition or how to define frustrated phagocytosis, because the underlying ideas, what can be tested as a tier testing strategy, is maybe working from the side of the research side, but it might not be the same kind of understanding when it comes from the in vivo experimentation and if you want to see similar effects. And also the question would be how to apply polydispersed nanoforms. So in our case, we worked with the D50 with the mean values. Also, Eleanor has said they've not considered the size distributions, which is a critical factor because this can in the end determine if you have this toxicity according to the fiber paradigm or not. And with this, I would be at the end of my talk. Yeah. Thanks for your attention, or if you have some additional questions, we are still available. What's there?
So these fiber structures, have you figured out, because we see them also when we work, but we are unsure if they leak fibers when they're in the lung fluid. So say that when you release, then and your body's working, will they distribute into smaller fibers?
This information actually we also don't have. We are just relying on the information what we get submitted along with the registration dossiers. So it's not that we have the studies on our own to see if they solute or not, or if they get separated. Maybe some fibers can separate from the rest as individual fibers, but here in this case of this thin tangled materials, so the question is what kind of mode of action this separated singular fibers then would show compared to this larger assembly structure which is still present. Oh.
Well, I would say thanks a lot for this quite intense, I would say,
Yes, sorry.
and comprehensive and deep in effectively also insight into the hypothesis evidence-based grouping strategies that have been developed. And of course, there are always limits of application and they need to be tested and the models need to be challenged in a way. If there are no immediate questions, I guess we have deserved some coffee. And with this, I would like to thank you.
Thank you for your interest in our training on behalf of the NanoCommons project team and the European Union Nano Safety Cluster. Have a nice day.